When you toss a ball into the air, it arcs smoothly back down to Earth. On a human scale, the fabric of space and time is incredibly stable, guiding massive objects along predictable, unbroken curves. Zoom in to the microscopic level, though, and that smoothness vanishes. The quantum particles that compose the universe are jittery, chaotic, and easily disrupted. A stray microwave pulse or weak magnetic field is enough to corrupt a quantum state. The particles undergo sudden bit flips and phase flips, causing their coexisting possibilities to abruptly collapse into ordinary, dead data. This leaves us with a profound disconnect, a robust physical reality built entirely out of a foundation that is prone to constant error and collapse. Computer scientists have been wrestling with this exact paradox for decades. Engineers trying to build functional quantum computers are stalled by the same microscopic fragility. Instead of a standard binary bit that sits firmly as a 0 or a 1, these machines use qubits. A qubit can exist as both a 0 and a 1 simultaneously. This provides massive processing power, but it makes the system sensitive to the slightest outside interference. In 1995, mathematician Peter Shor proved that these fragile machines could actually work. He developed quantum error-correcting codes, mathematical schemes that detect and fix corrupted qubits without directly measuring or collapsing them. The core logic of Shor's code relies on redundancy. A single vital piece of logical information is hidden across a redundant network of entangled physical qubits. If one qubit is corrupted, the system checks the network and performs corrective surgery, keeping data intact. In 2014, physicists realized that gravity works according to this exact same principle. In certain theoretical universes, the interior geometry only stays stable because it distributes its information across the boundary, like an error-correcting code. To test how this works, physicists use a theoretical playground known as anti-de Sitter space, or ADS space. It's a mathematical toy universe with negative vacuum energy, used to safely isolate and study the rules of quantum gravity. In 1997, physicist Juan Maldacena proved that this specific toy universe functions like a hologram. In Maldacena's model, the 3D interior fabric is projected by a flat, 2D quantum boundary. Reconstructing a single interior point requires just over half of that boundary. You can delete large sections and the point remains anchored, exactly like Shor's code protecting a central qubit. This suggests that space-time is not a primary ingredient of the universe, but a secondary effect secured through the deep redundancy of quantum error correction. The following year, researchers developed a mathematical model called the Happy Code to map exactly how this error correction translates into physical geometry. In the Happy Code, a single point of space-time is treated as an individual mathematical unit that requires specific entanglement connections to its neighbors to remain stable. Boundary entanglement dictates how these units click together. This geometric cascade builds the bulk interior, tiling space piece by piece out of the void. Space-time behaves like a fabric woven from these redundant strands of entanglement, maintaining its own geometry through constant internal error correction. There is one place in the universe where this robust code is pushed past its limit and physically crashes: a black hole. In the language of error correction, a black hole represents the breakdown of correctability. The gravitational collapse creates an overwhelming accumulation of quantum errors that the local geometry can no longer fix. The black hole acts as a sink for physical ignorance, a region where the universe's fabric can no longer sustain its own architecture. In 1974, Stephen Hawking noted that black holes eventually evaporate, which triggered the information paradox. If a black hole swallows physical data and then disappears, that information might be permanently deleted from the universe. Treating space-time as an error-correcting code provides the mathematical tools to rescue this lost information. Because the universe operates on a holographic backup mechanism, information falling into a black hole is inherently protected, mirrored, and saved on the quantum boundary. As the black hole evaporates, researchers now suspect that data leaks back out through miniature strands of entanglement. These microscopic wormholes bridge the inside of the black hole to the outside, allowing the data to survive the crash. Our reality emerges from a vast underlying computational network that is continuously processing and correcting itself to sustain the world we see.